Imagine this. You're falling, but not like any fall you've ever experienced. There's no wind, no sound, just you floating in the absolute darkness of space. And ahead of you, a black hole. The most destructive force in the universe, a cosmic monster so powerful, not even light can escape its grip. As you get closer, something impossible starts to happen. Your feet begin stretching, longer and longer. Your body pulls apart like taffy. This is called spaghettification, and it's just the beginning. Because once you cross that invisible line, the event horizon, there's no coming back, ever. So what really happens if you fall into a black hole? The answer is far stranger than you think. Welcome back to Beyond Our World, where science meets mystery. I'm your host, and today we're diving into one of the most terrifying yet fascinating questions in all of physics. What happens if you fall into a black hole? This isn't science fiction, this is real science, based on Einstein's equations, quantum mechanics, and decades of research by the world's brightest physicists. And trust me, the reality is way more mind-bending than any movie. If you're new here, we explore the greatest mysteries of space and the universe. From black holes to aliens, from unexplained phenomena to cutting-edge science. Make sure to subscribe and hit that notification bell because we upload new space mysteries every Monday, Wednesday, and Friday. Now, before we talk about falling in, we need to understand what a black hole actually is. Because despite the name, it's not really a hole at all. Let's start at the beginning. A black hole is what happens when gravity wins. Completely, totally, forever. When a massive star, at least 20 times the mass of our sun, runs out of fuel, it can no longer fight against its own gravity. The core collapses. In less than a second, all that mass compresses into an impossibly small point. And I mean impossibly small. We're talking about the mass of several suns squeezed into a space smaller than an atom. That's called a singularity. And around that singularity forms the event horizon. This is the point of no return. Cross it and the gravity is so strong that you would need to travel faster than light to escape. But nothing can travel faster than light. Not you. Not a spaceship. Not even light itself. That's why it's called a black hole. Light goes in, but it never comes out. Now here's what makes this even more fascinating. Black holes aren't rare cosmic curiosities. They're everywhere. Our own galaxy, the Milky Way, contains an estimated 100 million black holes. And at the very center of our galaxy sits Sagittarius A-star, a supermassive black hole with a mass of 4 million suns. We've even photographed it. In 2022, the Event Horizon Telescope captured the first image of Sagittarius A-star. That glowing ring you saw in the news? That's matter super hot as it spirals to its doom. The black part in the center? That's the event horizon. The point where physics as we know it breaks down. So what would it actually feel like to approach a black hole? Let's say you're in a spacecraft, moving toward a stellar mass black hole, about 10 times the mass of our sun. From far away, it might not look like much, just a dark spot against the stars. But as you get closer, you'd notice something weird. The stars behind the black hole would appear to bend around it. This is gravitational lensing. The black hole's gravity is so strong it literally warps space itself, bending the path of light. Einstein predicted this in 1915, and we've observed it countless times. It's real. As you move closer, you'd see the accretion disk if the black hole has one. This is matter, gas, dust, maybe the remains of a star, spiraling inward at incredible speeds. The friction heats this matter to millions of degrees. It glows brighter than entire galaxies. If you were close enough, the radiation alone would kill you instantly. But let's say you have magical protection from radiation. Let's focus on the gravity. Here's where things get truly strange. At some distance from the black hole, you'd start to notice something terrifying. The gravity at your feet would be noticeably stronger than the gravity at your head. Remember, gravity gets stronger the closer you are to a massive object. And when you're near a black hole, that difference over just 6 feet of your body becomes extreme. This is tidal force. And near a black hole, tidal forces are monstrous. Your feet, being closer to the singularity, would be pulled harder than your head, much harder. you'd start to stretch. Scientists call this spaghettification, and yes, that's the actual scientific term. Your body would elongate like a piece of spaghetti. At first, it might just feel like extreme pressure, like being on a medieval torture rack. But it gets worse, much worse. Your bones would stretch, your muscles would tear, your blood vessels would rupture. And because the pull at your feet is so much stronger than at your head, you wouldn't just stretch vertically. You'd also compress horizontally. Squeezed from the sides, stretched from top to bottom, eventually you'd be torn apart at the molecular level, atom by atom. This would happen before you even reach the event horizon. For a small black hole, like the one we're describing, you'd be spaghettified millions of miles away from the event horizon. You'd die long before you cross the point of no return. But here's the fascinating part. The bigger the black hole, the gentler the approach. For a supermassive black hole, like the one at the center of our galaxy, the tidal forces at the event horizon are actually quite weak. The event horizon of Sagittarius A-star is about 12 million miles across. At that scale, the difference in gravity between your head and feet would be negligible. You could, theoretically, cross the event horizon alive, conscious, aware. You wouldn't even feel anything special as you passed through. No wall, no barrier, just empty space. But you'd have crossed into a region of space-time from which you can never escape. Now let's talk about time, because here's where black holes get truly mind-bending. According to Einstein's theory of relativity, time is not absolute. It flows at different rates depending on how fast you're moving and how strong gravity is. Near a black hole, gravity is so intense that time itself slows down. This is called time dilation, and it's not theory. It's observed fact. GPS satellites have to account for time dilation because they're farther from Earth's gravity. The difference is tiny, but it's real. Near a black hole, the effect is extreme. Imagine you're falling toward the event horizon and your friend is watching from a safe distance. From your perspective, you'd fall normally. You'd see your friend. You'd see the universe. Everything would seem relatively normal, aside from the increasing tidal forces. But from your friend's perspective, something very different would happen. They'd see you slow down. As you got closer to the event horizon, you'd appear to move slower and slower. Time for you, from their point of view, would be passing incredibly slowly. And as you approach the event horizon, you'd appear to freeze, almost stop completely. The light from your body would stretch, becoming redder and redder, shifting beyond visible light into infrared, then radio waves. You'd fade from view. From your friend's perspective, you'd never quite reach the event horizon. You'd just get dimmer and dimmer, frozen in time, until you disappeared. But from your perspective, you'd cross the event horizon in finite time. You'd fall through. And then, things would get even stranger. Once you're past the event horizon, the rules change completely. Outside the event horizon, moving away from the black hole is difficult, but possible if you have enough speed. But inside, the singularity isn't just in front of you. It's in your future. Literally. Space and time swap roles inside the event horizon. Outside, you can choose which direction in space to move, but time only goes forward. Inside, you can't choose to avoid the singularity any more than you can choose to avoid next Tuesday. It's inevitable. You will hit the singularity. There's no escaping it. Not with rockets. Not with any technology. It's as unavoidable as tomorrow. But what would you see as you fell? This is where our knowledge becomes uncertain, but physicists have some fascinating theories. You might see the entire future history of the universe outside the black hole play out in fast forward. Because of the extreme time dilation, light from the outside universe would be blue-shifted, compressed. Billions of years might pass outside while only seconds pass for you. You could potentially watch stars die, galaxies collide, the universe itself ending, all in the brief moment before you hit the singularity. Or you might see nothing but darkness. The photons from outside might not be able to catch up to you as you plunge inward faster and faster. Some physicists suggest you'd see the inside of the black hole illuminated by Hawking radiation, a quantum effect we'll discuss later. The truth is, we don't know. No one has ever been inside a black hole and come back to tell us. And no one ever will. And then you'd reach the singularity. This is the center of the black hole, where all the mass is concentrated. According to our current understanding, it's a point of infinite density, infinite gravity, where the equations of general relativity break down and give nonsensical answers. At the singularity, you'd be crushed to infinite density. Your atoms would be destroyed. The very concept of you would cease to have meaning. But here's the thing. Most physicists don't actually believe singularities exist in the way our math describes them. When your equations give you infinities, it usually means the theory is incomplete. We know general relativity works brilliantly for describing gravity on large scales. But at quantum scales, at the heart of a black hole, we need a theory of quantum gravity. And we don't have one yet. String theory, loop quantum gravity, and other approaches suggest the singularity might not be a point of infinite density. It might be a region of extremely high but finite density. Or it might be something else entirely, a gateway to another universe, a white hole spewing matter out somewhere else, a region where time flows backward. These aren't just wild speculation. These are serious ideas being explored by physicists. The truth is, we simply don't know what happens at the center of a black hole. Our best theories fail us there. But wait, there's more. In 1974, Stephen Hawking proposed something that shocked the physics world. He suggested that black holes aren't completely black, they emit radiation. This Hawking radiation comes from quantum effects right at the event horizon. In the quantum world, pairs of particles and antiparticles constantly pop into existence and annihilate each other. This happens everywhere, all the time. But near the event horizon, something different can occur. One particle falls into the black hole while its partner escapes. From the outside, it looks like the black hole is emitting radiation. And here's the kicker. This radiation carries energy, and that energy comes from the mass of the black hole itself, which means black holes can evaporate. Very, very slowly. For a stellar mass black hole, the evaporation time is far longer than the current age of the universe. We're talking 10 to the power of 67 years. But for tiny black holes, if they exist, evaporation could happen much faster. And if black holes evaporate, that raises a mind-bending problem, the information paradox. According to quantum mechanics, information cannot be destroyed. But if you fall into a black hole and the black hole evaporates, what happens to the information about you? Does it disappear? That would violate the laws of quantum mechanics. Or is it somehow encoded in the Hawking radiation? This paradox has been one of the biggest unsolved problems in physics for 50 years. Recent work suggests the information might be preserved on the event horizon itself, encoded in a holographic way. But we're not certain yet. Now let's talk about something even more speculative: wormholes. Some solutions to Einstein's equations suggest that black holes might be connected to white holes, hypothetical objects that spew matter out instead of sucking it in. The connection between them would be a wormhole, a tunnel through space-time. Could you travel through a black hole and emerge somewhere else? Maybe another part of our universe. Maybe another universe entirely. The math allows for it. But the physics is brutal. Most wormholes, if they exist, would be incredibly unstable. They'd collapse before anything could pass through. You'd need exotic matter with negative energy to keep them open. We've never observed negative energy matter. Some physicists think it might be possible using quantum effects. Others think it's forbidden by the laws of physics. And even if you could keep a wormhole open, the tidal forces would likely destroy anything trying to pass through. Unless it's a supermassive black hole wormhole, where tidal forces are weaker. But we have no evidence that wormholes exist. They're mathematically possible, but that doesn't mean nature uses them. It's one of the greatest open questions in physics. Here's another wild idea. Some versions of string theory and quantum gravity suggest that what we call a black hole singularity might actually be a point where our universe connects to other dimensions. We live in 3 dimensions of space and 1 of time, but string theory requires up to 11 dimensions. Most of these extra dimensions are curled up so small we can't see them. But inside a black hole, maybe those dimensions unfurl. Maybe this singularity is a doorway to a higher dimensional space. This isn't just science fiction. These are legitimate physics papers published in peer-reviewed journals. We don't know if they're right, but they're being seriously considered. The point is this: black holes are windows into physics we don't yet understand. They're nature's laboratories for extreme conditions. By studying them, we learn about gravity, quantum mechanics, the nature of space and time itself. So could humans ever actually observe what happens inside a black hole? Not by going in, obviously. But what about sending a probe? Even that wouldn't work. Remember, once something crosses the event horizon, no information can come back out. Any probe that entered couldn't transmit data back to us. From our perspective outside, it would just freeze at the event horizon and fade from view. We could never know what it experienced inside. But we can study black holes from the outside. The Event Horizon Telescope, which took the first pictures of black holes, is being upgraded. Future observations will reveal more detail about the event horizon, the accretion disk, the jets of matter that some black holes shoot out. We can study how matter behaves in extreme gravity. We can test Einstein's equations in the strongest gravitational fields in the universe. We can look for evidence of Hawking radiation, though it's so faint we haven't detected it yet. And by studying the gravitational waves from colliding black holes, detected by LIGO and other observatories, we can learn about what happens when space-time itself is violently disturbed. Every time two black holes merge, they send ripples through space-time that we can measure. It's incredible. In 2015, we detected gravitational waves for the first time. Since then, we've observed dozens of black hole mergers. Each one teaches us something new. Here's what we know for certain. Black holes are real. They exist throughout the universe. We've photographed their event horizons. We've detected their gravitational waves. We understand a lot about them. But the most important questions remain unanswered. What happens at the singularity? Do wormholes exist? Can information escape? Is there something beyond the event horizon that we don't understand yet? These mysteries drive modern physics. And one day, maybe, we'll have the answers. For now, all we can say is this: if you fell into a black hole, your fate would be sealed. For a small black hole, you'd be torn apart long before reaching the event horizon. For a large one, you'd cross the event horizon intact, watch the universe age and die in fast forward, and then be crushed at the singularity. Or maybe, just maybe, you'd find something else entirely, something we can't even imagine yet. So what do you think happens inside a black hole? Infinite crushing? A gateway to another universe? Or something even stranger? Drop your thoughts in the comments below. I love reading your theories, and some of you come up with incredible ideas. If you enjoyed this journey into the most extreme objects in the universe, smash that like button. It really helps the channel grow. And make sure you're subscribed with notifications turned on, because we're posting new space mysteries every Monday, Wednesday, and Friday. Next time, we're exploring Oumuamua, the mysterious object that flew through our solar system in 2017. It moved in ways that don't match any asteroid or comet. Some scientists think it could be an alien probe. We'll examine all the evidence. Until then, keep looking up. And maybe be grateful you're not falling into a black hole right now.